All right, guys, so what we're looking at here is the review for test 4. Now, unlike the other reviews that we've done so far, this review I'll actually go over all of the problems while we're doing it rather than having it filled out ahead of time. So just be aware of that as you kind of watch this. We'll cover all the problems in this. This one's actually a little bit easier, a little bit shorter, so let's dive right in. Here we go. So for the first function, we have f of x equals 6x squared minus 12x minus 7. And I want to know on what intervals is this function increasing, decreasing, and whether they are maxes or mins. In order to do that, what we're going to have to do is we're going to have to use the first derivative in order to find out all of that information. So the first thing we always want to do is find our critical points. The way that we find our critical points is we set the first derivative equal to 0 and solve it, and in this case, we find that our critical point is at x equals 1. Now what that means is that is going to be where we're going to have either a max or a min. So remember, we choose numbers on either side of that number. Like I'm going to choose like 0, and I'm going to plug that into the first derivative to indicate what is happening before we get to x equals 1 as far as whether the function's increasing or decreasing. And when I do that, I get a negative number. 12 times 0 minus 12 is equal to a negative number. So that means the function's decreasing up until x equals negative 1. Then I choose a number bigger than positive 1. Then I choose a number bigger than 1, like, 14. And I plug that in and I get a positive number. What that tells me is from 1 to infinity, the function will be increasing. So that's the first question, where is it increasing? Second question is, where is it decreasing? And then we want to know the x value of the critical point, so that's x equals 1, and we say whether those points are a max, a min, or neither. In this case, because we go from decreasing to increasing, we have a minimum at that point. So again, hopefully that makes sense. Not that big of a deal. That one's not that bad. On the next one, we're asking about concavity. So 4, 5, and 6 are all asking about concavity. So I need the second derivative for that. Well, in this case, the second derivative is 12, which if I take 12 and I set it equal to 0 to try and find my possible points of inflection, there are none because 12 never equals 0. So number 6 is actually the first one we can answer here. There are no points of inflection. On numbers 4 and 5, if we have to indicate where the function is concave up and concave down. When I look at this, since the number 12 is a positive number, that means the second derivative is always positive. So that means the original function is always concave up. So we'd say from negative infinity to positive infinity, which means it is never concave down. And again, hopefully that kind of makes sense as to why those things are true. And then number 7, if we want to draw the graph, remember we just need to graph all of our important points. The only one we have here is x equals 1. That's going to be a minimum. So I plug 1 in for x, and I get 6 minus 12 minus 7. That gives me, oh man, I chose another bad one when I created this function. That gives me negative 13. So I know the point 1, negative 13 is on the graph. So I realize that's not actually on here, but I'm going to put 113 down there. And I know more or less what this function looks like just by knowing that it's concave up the whole time, decreasing from negative infinity to positive 1. Shoot, this needs to be shifted over there. So it's over here. Gosh dang it. My eraser doesn't work very well, so we're just going to pretend like that other one doesn't exist. So it looks something like that. Let's see if I can erase that other one real quick. Oh, Parker, learn to use your stuff. All right. So there is, got rid of that. Knowing that at x equals 1, we've got ourselves a minimum. And again, just a rough sketch of the graph. Just make sure your points are labeled correctly. We're going to do the same thing for numbers 8, 9, and 10. The only difference is, like on this one, I get 3x squared minus 8x minus 3. This one's a little bit harder to factor. So I look at this, and what I have to do is I have to put 3x in one and x in another. And if you don't remember exactly how to factor these, there's multiple ways to do it. But it turns out that it's 3x plus 1 and x minus 3. Which means my critical points in this problem are at negative 1/3 and positive 3. If I look at the number line for that, so I'm going to go negative 1/3 and positive 3. Again, what I'm going to do is I'm going to plug numbers into the first derivative on either side of those to find out what is happening. Now, the one piece of advice I will give you is I would always recommend putting it into the factored form of the first derivative, just because it's easier to tell whether or not it's a positive or negative. Like if I plug in like -2, I get a negative times a negative, which would be a positive number, which means the function's increasing there. If I take a number like 0, I'm going to get a positive number and a negative number. That gives me a negative, and then a number larger than 3, like 15, something like that, I'm going to get a positive and a positive, which tells me that it's positive. Now again, I've warned you a little bit before, and this doesn't happen often, but you do need to check all of them. Do not assume it just goes positive, negative, positive every single time. So when I do that, in this case, I get that it's increasing from -infinity to -1/3, and then also we have a second place, 3 to infinity. Where the function is decreasing is from -1/3 to 3. So at our critical points, at x equals -1/3, we have ourselves a max. At x equals +3, we have ourselves a min, due to the fact that for the maximum, the function changes from increasing to decreasing. For the minimum, the function changes from decreasing to increasing at those critical points. For 11, 12, and 13, just like we did before, we need the second derivative. So the second derivative here is 6x minus 8. So what we're going to do to find our possible points of inflection is set that equal to 0. And you can simplify it down. You don't have to, but you get x equals 4/3 or 8/6. So there is a possible point of inflection. Now what we do is we put 4/3 on a number line, choose a number smaller than that and bigger than that. So I plug in 0, I plug in 22, doesn't matter what the number is. What I do when I plug in 0 is I plug that number into the second derivative, and I find out that I get a negative number. When I plug in 22, I get a positive number. Because this is the second derivative, this tells us where our function is going to be concave up or concave down. So from 4/3 to infinity, because the second derivative is positive, our original function is going to be concave up. From -infinity to 4/3, because my second derivative is negative, my function is going to be concave down. And again, we've gone over this before, and hopefully all of that makes sense. Okay, and then if we want to draw this, we just have to choose our points, and I'm actually going to let you do that on your own because I forgot to draw it ahead of time. So do that on your own. It ends up looking, the shape is, oh man, let's see, we've got max. So it goes like this, basically, and it's not in the right place, but it does something like this. And I think the numbers are super weird on this one too, and that's not exactly right. Man, that's way wrong, actually. But don't pay attention to what my picture looks like. Just draw that one on your own. I'm not too worried about whether or not you can plot the points. Just don't forget, for all of your x values, you need to find the y values that go with them. Okay? So don't forget that just by plugging those into the original function. And again, this is actually not what it actually looks like at all. What it looks like. The shape is right. The position is wrong. Everything is wrong other than it looks like that shape right there. All right, so now we're moving on to the table problems. So number 15 says, what is the minimum number of maxima that f of x will attain? Well, we talked about this before, but remember, anytime we're looking for a maximum, what we're saying is that the first derivative has to change from a positive value to a negative value. So I go hunting for that, and I see that at x equals 0, it's positive. At x equals 4, it's a negative number. So I see that there will be at least one of those, and this question's actually wrong. It shouldn't say what is the function value. It should say on what interval does that occur. And that's supposed to be from 0 to 4. Okay? And I know that because that is where the first derivative changes from positive to negative. To find a minimum, we look for the same thing. I look to see where we're changing from negative to positive. Well, that never occurs here, so that is going to be that never is going to happen because the first derivative never changes from negative to positive. Same thing being asked about points of inflection. Now you'll notice this time that at x equals from -3 to 0, it changes from a concave down to concave up. So there's one of them there from -3 to 0. There's also one from 0 to 3, even though it doesn't say that the second derivative is 0. It's positive here, it's negative here. So I look at it, I'm like, well, it changed again. Okay, and then I can't say that that happens for sure from 4 to 5. So there are two different places that those occur on those different intervals. Hopefully that kind of makes sense. Number 18 says, what is the average rate of change between x equals 3 and x equals 5? Well, remember, average rate of change is just y2 minus y1 over x2 minus x1. y2 minus y1 in this problem, f of x is another name for y, so we just go negative 3 minus 4, because these are the x values that we're talking about. So I look at the y values that are associated with those. Then I just put those over x2 minus x1, and I get negative 7 over 2. So negative 7 halves is my average rate of change here. On number 19, this is two different questions. What is the instantaneous rate of change at x equals 3? Well, I just go to 3 right here, and another name for the instantaneous rate of change is the derivative. So at x equals 3, it's 0. At x equals negative 5, when I look at that, I look at the first derivative, and that is 2. Okay? So, again, instantaneous rate of change just means what is the derivative at that point. Fancy way of saying it. We finally switched to the mean value theorem for the last couple problems. Now remember, the mean value theorem says that we can find the average rate of change between two x values on a function as long as the function is continuous and differentiable between those 2 points. Then we take the derivative and set it equal to the average rate of change to find out where the instantaneous rate of change would be the same as the average rate of change. So in order to do these problems, we need to know the derivative. So here the derivative is 10x. And we also need to know the average rate of change. Okay? So in this case, what I do is I say, okay, to find my average rate of change, we just barely talked about it, y2 minus y1 over x2 minus x1. So I've got 2 minus negative 1 on the bottom. On the top, in order to find the y values, I have to take those and I have to plug them in. So I take negative 1 and I plug it into the function and I get negative 2. I take 2 and I plug it into the function and I get 13. So what I have here is 13 minus negative 2. That's 15 divided by 3, so my average rate of change is 5. So now what I do, now that I've found my average rate of change, is I take 10x and I set it equal to 5. That's taking my derivative and setting it equal to the average rate of change. In this case, that is at x equals 1/2. So that is our answer for this particular problem. Okay? Now, on number 22, what we're going to do is we're going to say, okay, I'm going to take the derivative, g prime of x is equal to e to the x, and there's one part I'm going to actually have to help you with on this one. To find my y values that go with negative 4 and positive 4, I'm going to plug that in, so I get e to the negative 4 and I get e to the positive 4. So I'm just going to go e to the 4th minus e to the negative 4 over 4 minus negative 4. And when I put that into my calculator, I get, for that particular thing, I get 6.822. Okay? So that is my average rate of change. Now what I have to do is I have to set that equal to my derivative and solve for it. Now I know it's been a while since you've had to solve problems with e to the x, but what we do to get rid of the e is we take the ln of both sides. When I do that, I get ln of 6.8244, or 822, excuse me. When I put that into my calculator, I get that x equals 1.920. Now on the test itself, you're not going to have to worry about being able to solve an e question. I just want to make sure that we understand how to do that problem. The last problem on the review, why can't we apply the mean value theorem for this function? We have to know what that function looks like. So the absolute value of x looks like a v. The reason why I cannot use the mean value theorem from negative 3 to positive 3 is if I look at this function at x equals 0, I have a corner, which means between negative 3 and positive 3, there is a place that the function is not differentiable. It's not differentiable at x equals 0, which means I cannot take the derivative there, which means I can't apply the mean value theorem. So again, what we're looking for to make sure we can use the mean value theorem is on the interval in question, is the function continuous and differentiable? Here it was continuous, but it was not differentiable. Overall, this test, I hope you don't feel too bad about it. This test should be okay. If you have any questions about this test, please let me know. Otherwise, there's all your answers for you.